Okay, let's start. Okay, let's just wait. If the screen will go dark after like a minute or so.
Okay, but it will
Still be recording.
Okay, okay. Okay.
Like, yeah.
Do you have the lights?
Like this?
Yeah. Is it visible now?
Yes, it is visible. Also you. But if you go more over there, you will not be visible.
Okay, so I have to stay in this.
Yes, better. Yes.
Sí, sí, sí.
So are we waiting or?
I think that's all.
Okay, probably.
Because if they have an exam,
Okay, then I'll start. Okay. So, hello guys. Today I'm going to give a talk on phenomenal space-time and critical brain graph dynamics. Now this sounds like a mouthful, but I'm going to explain what everything means. Initially, this lecture was supposed to be about graph theory only. But then I decided instead of explaining the mathematical formalism of graph theory, which will bore you to death, I will just pick up a very interesting problem, the problem of explaining consciousness, and then try to adapt this theoretical framework to this problem so that we could make sense of it. And during the course of the presentation, the pieces of the jigsaw will gradually fit together, and at the end you will have a very holistic and coherent picture. And in this lecture, I've integrated the latest research in consciousness studies. So a lot of the things will be very new to you, even if you are an expert of the field. So let us begin with framing the problem. So like all problems in science, consciousness is also amenable to research methods, but there is one underlying assumption which faces all kinds of consciousness research, which is that we are looking at consciousness from a third-person perspective. We are using the tools of science in order to study it from an objective phenomena. But consciousness intrinsically is a subjective phenomena. And while there are many definitions of consciousness, the one that I'm going to focus on is the most universal and minimal definition of consciousness, which relates with its phenomenology. Like, what is it like to experience anything? The feelings, the colors, the sounds, the textures that we experience in our subjective awareness, all of these form the minimal subjective character of consciousness, which is known as phenomenology. So we are going to be studying consciousness from the phenomenological perspective. So now we have certain tools of brain research that we apply to every phenomena to study it. But the problem with consciousness is that how does brain activity give rise to subjective experience, which is also colloquially known as the hard problem of consciousness. So in every day and age, we always have certain metaphors that are derived from the current technology that we have in order to explain the brain as a machine. So in the 19th century, we had the steam engine, and even before that, we had, if you read Descartes' philosophy, he viewed animals and also human beings as mechanistic systems of interacting parts which give rise to a collective behavior. So in this sense, the brain was likened to a machine, and after some period of time, the metaphor started changing. We came to view the brain as a steam engine, and later on, in the 20th century, the prevailing metaphor, which has also crossed over to the 21st century, is the computational metaphor, which views the brain as producing consciousness by representation and encoding. So neural activity in the brain implements information processing. There are a lot of cognitive algorithms. This information gets integrated, differentiated, lots of sensory modalities get bounded together in one coherent experience, and that is how it is thought that the brain operates, as a computational system. And what is important in this is the buzzword encoding and representation. So our conscious experience is said to be like an internal representation of the external environment that the brain encodes computationally using symbolic representation. So we are going to see how well this metaphor holds up to the latest research, and if there is an alternative approach which will allow us to approach the problem from a different perspective. So what we look for usually are the neural correlates of consciousness. these are basically our explanatory entities from the third person perspective. Because consciousness is a first person subjective phenomena, but on the objective side, the side that science deals with, we are going to look at patterns of neural activity and try to correlate them with our subjective experience. So the consciousness studies actually deals with subjective reports of experience in carefully designed experiments and then correlating that activity with the actual brain dynamics. So this also has one assumption, which is that space and time is objective and it is already given. So in order to find where consciousness resides, we look at certain brain regions and the functional connectivity of those brain regions to localize where experience resides. But I'm going to argue that this approach is actually holding us back from actually getting a holistic picture of how consciousness actually works. So experience unfolds in physical space and clock time. This is one of the implicit assumptions that we have. So then, the alternative approach is to take phenomenology seriously. So this is Husserl, and according to Husserl, we should study consciousness from the inside, from the first person reports, which means that consciousness is first given to every subject personally. Before we apply the tools of neuroscience or try to study brain activity, we try to look at experience through introspective reports and try to find out how it is structured. Like, we find out that it already has a gestalt character. Like, to sum, the whole is more than the sum of its parts, which I'm going to explain on the next slide. So it is immediately given to us. It has a coherent, systematic, holistic, and continuous structure. If we find out how this structure is implemented in a mathematical representation, then we can use this principle of mathematical isomorphism to map this structure onto neural mathematical representations. So like, this phenomenology which will actually constrain what kinds of explanations we can derive from our neural data. So the structure of experience will be translated into a mathematical object, either in the static or the dynamic sense, using the tools of graph theory. And then it's going to be compared to what substrates in the physical architecture and the dynamics of the brain can actually support and constrain these processes such that the mathematical isomorphism is preserved. So this is going to give us a constraint from the outside even before we look at the neural data. It's going to give us a theory in which we could interpret this neural data. Because in neuroscience research, what we have is that functional correlations are mapped using statistical correlations. So like, there is one approach in which we just look at the statistical correlations and try to view them without having an explanatory theoretical framework in order to interpret them. But in this framework, we will use this constraint of the mathematical isomorphism and then look at the data. So what is a Gestalt theory? So Gestalt theory was actually, like, it follows from the work of Husserl, but actually was developed by Merleau-Ponty and also certain American pragmatists like William James. So the Gestalt theorists actually say that experience is never isolated colors or free-floating sounds or like unbound features. And the greatest, most intuitive explanation of that is like bistable images. So if you see these images, they're actually two very holistic representations that your brain can form of the same image, but the underlying representational framework remains the same. They are the same pixels, and if you encode this into a computer, like the internal representation, if you view the brain as representing information, the representation stays the same. But somehow, the way all of this information is coherently integrated into a holistic picture, that actually differs. And this is also the phenomena behind facial blindness. For example, it is said that like Brad Pitt, for example, cannot recognize faces as well because it is thought that he has this disease in which you can see the face, but you can also isolate the features and describe the nose and the mouth and the lips and everything, but you cannot integrate everything together into a coherent gestalt. So this gestalt character actually means that we need something more than representation in order to represent experience. And this is actually following from our phenomenology first approach, in which we have to find some physical process which can instantiate this kind of gestalt character. And the flip side of this, on the third person perspective, is what is known as multisensory integration, which we also studied, in which, for example, if you see a red ball bouncing, the red ball as an object is a coherently integrated phenomenal percept, which is actually changing in space and time. When it is approaching you, it is changing its size in your awareness, but your brain still processes it as a single object, a single ball. So like how is this feat accomplished in which motions, shapes, sound, color and everything is coherently integrated into a gestalt. So gestalt is not only in the static representations but also in our dynamic percept tracking or object recognition. So how is everything accomplished? So then we come to the initial assumption that we have that everything unfolds in an objective space and time. And like this is going to sound radical, but it is actually a very old idea by Immanuel Kant that the subjective space and time that we have, like everyone's own coordinate system. For example, if I'm standing here, the origin of my coordinate system is myself, and I'm measuring the distance to everybody else in my phenomenal awareness according to my own origin system. Like I'm relating every distance to myself. So like I'm at the center of my coordinate system and I have this local space. At the same time, all of you also have your own local space and time. This actually explains how phenomenological reports of like time passing are also changing depending on how the brain is processing information. So like sometimes we think that time is passing slowly or like fast, but when you can compare it to a clock, like our reports do not exactly match the clock time. So like according to Kant, like the space and time that we have internally is like a form of intuition. Instead of space being like a container in which experience unfolds or trying to locate experience inside specific brain regions, the brain constructs its own space and time, subjective space and time. So like we won't go much into Kant's philosophy and its other ideas, but like we will just depart from this point in which the brain has to construct its own representational system in which to interpret and bind the gestalt character of experience, which is the subjective space and time. So it is not a representation of physical space and time, it is an internal coordinate system in which is actually part and parcel and constitutive of experience. So why is localization of brain activity not enough? So here we have the dynamically unfolding functional connectivity of the brain. So what we see is that the same experience that we have phenomenologically is implicated in many different areas, and each of those many different areas are implicated in many different experiences. So it's very hard to like assign a function to a specific brain area, but we have done this to some degree when it does not come to consciousness. For example, the entire visual processing system from V1 to V5 definitely has the role of visual processing. But right now we are talking about phenomenology, how experience unfolds. So like associating different areas to certain types of percepts is like a very difficult job to do because of this problem, because of the dynamically and functionally reused repertoire of activity that we observe in the brain. So experience cannot be mapped to places, it must be mapped to patterns of coordination in the functional sense. So we need a new descriptive language in order to like approach this problem, and in order to have a representation for the mathematical isomorphism that I was talking about. So these local elements in objective space cannot explain this holistic binding character, the simultaneity of experience and its gestalt coherence. So we need a mathematical tool, and graphs are like a very good candidate, because if we look at the Human Connectome project, the graphs that are used in that kind of a problem are mapping the structural connectivity, the physical distance, the Euclidean distance between different neurons and their structural connectivity. But we can also use and adapt graphs in the functional sense. So the graphs can describe the structure without assuming the geometry. And if this gestalt unity is primary, then relations and not parts must be fundamental in our phenomenological experience. And this brings us to like the definition of like a simple graph. So the nodes can represent a lot of different things. They can be neurons or like neuronal assemblies or different cortical regions, but we are still looking at this from the structural standpoint. From a more abstract functional standpoint, we can also have coherent, transiently stable patterns of activity which can act as like limited time nodes. So like the only thing that you require for a node is like temporal persistence, but this temporal persistence does not have to be like spread over the entire region of activity. It can also be transient. It just has to be stable for a little time in order to act as a node. And the edges can represent the functional interaction, and something called the RTP, which is very different from the way that we are currently studying functional connectivity, which I'm going to explain in the next slides. and how these different regions of functional activity are synchronized with each other. So two distant regions can be close if they interact reliably. So this is very different from the concept of space that we have in metrical space, in which the distance is actually isomorphic to the geometry. But in this, the distance is actually isomorphic to participation in the same pattern. And our working assumption is that what appears in phenomenology together, like I form a percept in which every element is related to everything else. So what appears closer together is also functionally close in the temporal brain dynamic sense. So this is our working assumption. So this mirrors how experiences feel close or distant independent of their physical layout, like in the brain, because a lot of different regions are implicated in a wide variety of different tasks. So why graphs alone still cannot explain all the features of consciousness. So there are some other features, like for example, you must have experienced an insight or an idea suddenly clicking in your mind. Like you get the idea at once, you get insights at once. So there are like these stable and abrupt discontinuous changes in the way that your brain is forming perceptions. So like these graphs unfold continuously, even if you have dynamics on the graph in which the graphs themselves are changing, these changes can be described in a very continuous step-by-step manner. But in our consciousness, the way that we suddenly perceive an object or like have an insight, we have like sudden transitions in experience. And these are very natural. When we look at a face, we don't count all the different regions and then process it like phenomenologically speaking, and then form a picture. The entire face appears at once in our awareness. So how does this happen? Like we come to the conclusion that graphs are insufficient. So we need to add another ingredient. The chemical X that we will use is statistical physics, and particularly thermodynamics and the science of order and disorder, or criticality. So we will see how criticality explains these features. We also experience multistability, metastability. So for example, whenever you are going to perform any action, there is always like this potential reservoir of potential actions that you can do, and they are all available to you as viable options. This actually grounds our subjective experiences of choosing, or like free will, for example. So metastability means that the system is at a state in which it has an equiprobable probability of landing into multiple different coherent attractor states. And a small perturbation can land it into any of those states. So we need this sort of metastability if we are to find these neural correlates of consciousness, because we experience them ourselves in our awareness. So let's include this statistical physics into our repertoire and like see how graph theory changes. So first, let us see why we need statistical physics. So our phenomenal experience has stable moments and these abrupt transitions. So this is a quote by Emanuel Wallerstein. When systems close to or far from points of equilibrium, they reach bifurcation points wherein multiple as opposed to unique solutions to instability become possible. So this is like a statement of this metastability that I was talking about. So any structure, any system with this structure has to have these thermodynamic properties, that it has to be an open system in which there is like constant influx of energy and matter. It cannot be a closed system, and it has to exist far from equilibrium, because in these systems we observe this kind of metastability, and we are going to see the reason for that. So if we have a closed system, we will have equilibrium because of the second law of thermodynamics. The entropy will always increase, and there is not going to be any structure or experience. So whatever the brain is doing, it has to be some kind of far from equilibrium open system. So it has to be realized by these dissipative dynamics, and I'm going to explain what that means. So this is James England, and he solved a problem which had been plaguing thermodynamics research and complexity science for a long time, which is that we as living organisms exist in like very low entropy states, and like we are very complex. And if you see the evolution of life, life has been tending towards more or less greater complexity, even though it can be argued that evolution does not have any preferred direction. But still, if we observe today's era from the Cambrian era, we can see that a lot has changed in terms of complexity. So if the universe is tending towards disorder and everything is maximizing entropy, then how can we have these completely ordered states? Like, doesn't this violate second law of thermodynamics? So what he actually mathematically showed was that these open systems are actually a very good instance of the second law of thermodynamics, because they actually increase the overall disorder if you take the environment also into consideration along with the life. So for example, this self-organizing ability of life actually offloads entropy into the environment, and it increases the entropy of the environment in a very short amount of time. So if we have a time series, this is a very efficient process of generating entropy, because we are not viewing life in isolation, we are also coupling it to the environment. So the environmental entropy is actually vastly increasing in very short spans of time. So actually the way the universe found to increase its entropy in the least amount of time was to create complexity. It sounds paradoxical, but it is not. So it exports entropy to the environment. So then let us see how we can explain the transitions in consciousness which are very abrupt, such as an idea or an insight occurring. So energy flows according to paths that consume free energy in the least time. So free energy is like the analog of entropy, like it's the reciprocal relationship we have. And this gradual reconfiguration is thermodynamically efficient. So the most efficient way to offload entropy into your environment in a coupled system is to have paths that consume free energy in the least time. So like this can actually explain these abrupt phase transitions. This is actually the basis by which systems which are in the critical stage, which I am going to explain, are actually prone to having these kinds of discontinuous phase transitions, as they are called. Like for example, in this bistable image, your brain immediately has a phase transition and you either view it as a duck or as a rabbit. So it actually gives you access to like many possible futures. For example, this relates with metastability. So when the brain is at the critical state, which I have not explained but I will explain, the correlations between different areas actually break, and we are assuming that the brain is moving from a highly ordered state to a less ordered state. In this example, you can approach criticality from both directions, from disorder to order or from order to disorder. So in the middle you have this critical point. So these micro elements explore many relations, and this increases their informational capacity and combinatorial power. So combinatorial power has like a very intuitive relation with the metastability, and the information capacity increases because information transfer is actually maximized when you have like very high fidelity communication of information and also storage of information. So in highly disordered states, you don't have stability, but you have maximal like transmission of information. But it is not worth it because like you cannot store it. And in highly ordered state, there is like stable dynamic configuration of information, but like the transmission of information is impeded. So in critical systems, it actually operates at the edge of order and disorder, and this transmission capacity and this like memory capacity is actually at a sweet spot in the trade-off. So like then we have the process of non-ergodic graphs. So ergodicity is a phenomenon in which if you have temporal activity, like either you can take the average of a temporal sequence, or you can take an ensemble average at a specific point in time. So if the system is like non-history dependent, it does not care about its history, the ensemble average is always going to be equal to the temporal average. So this is going to give you an ergodic process. But what we are seeing is that the brain actually learns and reconfigures itself, and like it actually primes itself according to expectations. So the brain has to operate in some kind of a non-ergodic process, because if we just look at neural activity, it kind of looks random, but when you sample it with statistical correlations, what you actually find is that many of the neural activity patterns that we are finding are actually non-ergodic processes. So like the view that we have of memories and how memories are stored is that they are like stabilized patterns which are stored just like not exactly, but we actually think of the analogy of computers, in which it is like represented in the magnetic spins of the implementation system in your hard drive. But perhaps the brain does not work like this. Perhaps what happens is that if it is actually traversing a dynamic landscape of attractive possibilities, so partial activation lowers thresholds for familiar patterns. So like just like if you have a marble like on a sink and you just drop it, it actually spirals around until it finds the minimum point. So just in this, a partial activation of the system which actually bias the trajectory to follow a specific pattern and to land into an attractive. So in order to reconstruct a memory, you won't need the entire information of the memory together, assuming that the memory is like represented by these dynamically shifting attractor patterns. You just have to like have a partial activation, and the system dynamics themselves, due to thermodynamics, will drive the system into that lower energy state, and you can recover your information. So memory may not be stored content, but a bias in these relational dynamics. So this is actually an example of phase transitions. So if we see a horse at different speeds, the most efficient way for a horse to traverse is using like completely different kinds of gaits. So like we have trot, we have canter, we have like gallop, and like depending on the critical parameter that we have. So in criticality we have two terms. One is the critical parameter, and one is the there was like this order parameter. So the independent variable is the critical parameter. You vary that critical parameter, and then the order parameter, which is actually a holistic global variable. For example, temperature is actually an analog for an order parameter because it relates to the whole of the system. So if we view the gaits that a horse shuffles through, they have abrupt phase transitions. The phase transitions are not continuous, and like the order parameter of the type of gait is changing, and the critical parameter, which is the speed at which the horse is going, it actually has to be varied in order to have these different phase transitions. So if we combine statistical mechanics, thermodynamics with graph theory, we get complex network theory. So it actually allows us to model graphs near phase transitions, and where they have large scale coordination and emergent structure. So what matters are relations, coordination, and co-activation patterns. So this is an example of how we can like marry these graph theoretical concepts and these phase transitions together. So this is like an example of like percolation theory, in which every node has a certain probability given by P of like connecting to its neighbors, and like we can vary this parameter in order to like change the connectivity of the graph. Now the colored regions in this and this is like a zoomed out version of the same graph, is like connected regions. So percolation theory is like percolation relates to like a liquid flowing. So like you can imagine that if there was a liquid over there, since these regions are connected, it will actually form a pool. So if we see this graph, what actually happens is that if for lower orders of like P, what we have are very small, discrete, isolated regions of the graph. But as we keep on increasing P, the size of the regions increases. But at some point, you have an equal probability chance of like finding a specific size of the region. For example, if you're randomly dropped inside, you have an equal probability of like being close to a very large region or a very small region. So this actually brings us to the concept of criticality, where like at certain point, what will happen is that the whole graph will blow up, and there is going to be like very, very large continuous regions. But we are mostly interested in the critical point. So what happens in the critical point is that it happens between order and disorder. So the systems at criticality are neither rigid nor random, and like the regime supports maximal flexibility with coherence, and we are going to see how that happens. So criticality can be a like an operational regime for the brain. For our mathematical isomorphism, whatever neural substrates we find for consciousness have to have, like it's not necessary and sufficient, but perhaps it can be argued that it is necessary for conscious states to be enacted on some critical kind of dynamic and functional architectures. So if consciousness requires this maximum flexibility of choice, unity, criticality, phase transitions, we need something like criticality in the brain. So this actually relates with fractals. Now this is really cool. This is like actually zooming into the Mandelbrot set. And what we have is that on the right side, we have scale and variance. So if you like take a region of the graph and like you embed it in a bigger region, it's going to look the same. So like no matter if you are placed inside and you are asked to find the absolute size of the region that you're in, there is no way that you can find that out, because every region, if you zoom in or zoom out, it looks the same. So there is like this vast scale and variance. And what this actually implicates is that if you have vast scale and variance at every level, you are actually going to have power laws. Now we're going to explain what power laws are. So like if you look at the left side, what you have is that if you want to express this insight that you are going to find similar structures at every scale, the K is the scaling factor, and like f of x can represent like anything. Like for example, in that percolation example, the size of the regions that you will find at x is like the absolute scale. And if you scale it up and you take the ratio, so like the size of bigger and smaller regions taken as a ratio is conserved across all scales. So it is going to be a function of g of k. Now notice that this g of k does not have x. So that means that it is not dependent on the absolute size. Now the only kind of function that obeys this mathematical equation is the power law. So in the power law, what you can see is like, if I move the slide, so wait, there was this animation. Yeah. So if you like zoom in and zoom out on the scale, this power law is like preserving its shape, while this exponential is changing its shape. So like we can, wherever we will see criticality, this will give us a fingerprint. Like observe the brain, find out which patterns are power law related. And this power law is going to give us scale invariance and by definition criticality. So this allows us to look for and hunt for criticality in brain dynamics. So it also has other properties. For example, in this Ising model, what we have are magnetic spins. So they have different variations of how correlated they are. So like when they are very hot, they have low correlation, and when they are very cold, they also have low correlation, even though like they look stable. But in both ends you have low correlation. But in this critical state you have high correlation. And this high correlation is actually related with the critical temperature. So if you measure the correlation length across like scales, what you can see is that the T cold and the T hot are like, they are not achieving like these maximal levels of correlation. But in the T critical, even though the correlations are decreasing with the distance, as should be the case, still the absolute graph is like higher than the other graphs. So in the phase transition, what you have is that this correlation length actually reaches like a discontinuous transition, a phase transition between order and disorder. And if you see this, like you can propagate information effectively using this. And what actually happens is that if you model this graph in functional activity and you change it and morph it in a way that it becomes a feed-forward network. So this does not change the network in an absolute way, it just changes the scale. You are applying a linear transformation on the graph. So like you can actually visualize activity propagating forward. So in order to have informational fidelity, what you need is that if some activity reaches like your neuron, imagine you're a neuron, or like you are this line of neurons, you need to determine where it is coming from. So if you see these three regimes, in the first regime what you have is that the critical parameter has a value of 0.5, which is very low. So the information that is traveling is like dying out on the way. And if you have like the critical parameter as 2, the information is traveling, but like it is saturating itself so much that when it reaches the end, like you cannot call it information because you don't know where it came from, how it started. Because every time it starts randomly, it just approaches this regime at the end. Every neuron activates. But if it is 1, what you're saying is that you can actually determine the pattern of how these are lighting up and use a mathematical model to reconstruct where it came from, because it actually has correlations which are preserved through time. So just like we have scale invariance, we also have this like message identity, and its reconstruction actually works very well when you are operating at criticality. So the brain also needs this, because otherwise the information that the brain is sending, it won't make sense at the recipient end. So then we have the resting state. So the resting state is not just the background activity, it's actually very, very complex. And actually we have a concept called the neural avalanche, where these local activities of these neurons actually form an avalanche which spreads to the rest of the brain or to a very large region. So these neural avalanches have been already observed to exhibit these power law statistics, which means that they are operating at criticality. So the critical regime is like a very special state. So even though the resting state looks like random, it is not, because it is like following these power laws and is operating at criticality. So the brain activity shows this scale reorganization, and there is evidence that it is like operating at criticality, and this is what allows the resting state to explore a wide repertoire of possible states that the brain can land into. This is the only way it can do that, if the resting state is operating at criticality, and it is poised near multiple possible transitions. So now circling back to phenomenology, like we have rapid reconfiguration of brain activity without structural rewiring, and this needs an explanation. And we have the coincidence of integration, the Gestalt character, and segregation, where in your phenomenal experience you have multiple different qualities integrated at the same time. So at the same time you need to have like maximal diversity and maximal integration. The critical regime is actually very good for implementing such a system. And you have discrete yet very flexible experiential states. So this can have a very natural substrate for phenomenal space-time, our internal coordinate system. So these are two brothers, like they are called the Finkelkreuz brothers. So they have this theory called, which I have mentioned in this paper, which we are going to see for the rest of this lecture, in which consciousness is a phenomena in the operational architectonics of brain organization, which is a term that they coined. So they actually proposed this term of the phenomenological space-time, which was actually mentioned in the title of this talk. So what they are saying that criticality alone, even though we have like integrated a lot of different theoretical methods, like we have graph theory now, we have thermodynamics, we have criticality, we have network theory, but still brain activity, even if it's modeled by these theoretical paradigms, still does not explain consciousness, because consciousness is still more complicated. And let's see why it is more complicated. So, like, what is the true unit of mind? If we only look at it from a third person perspective, a natural idea that comes to mind is that it is a neuron. Like a neuron is like a very mini brain, sort of like a mini brain. It's like a cartoon representation of a neuron. So what they actually propose is that in order to have a unit of mind, and mind is different from the brain, so mind relates with the internal subjective sense of like perception instead of like sensory integration. So it is a temporally stabilized field configuration. So what they propose is that consciousness is has this nested character in which these percepts organize themselves into higher and higher degrees of abstraction. So for example, if I look at a room, I can break this room down into like different objects, and if I look at each object, it will also have a microstructure. So you will have this nested Russian doll type character all the way down. So like still, even if when we have criticality and all these other theoretical concepts, we have still not explained how these objects like cohere together in a nested fractal manner. So, but we have some clues, and let's see how their theory actually informs us. So the operations that they have in their theory are not representations. So what they are saying is that they define this mathematical function which is autopoietic. Autopoiesis means that the activity of a system is itself generating the conditions for the propagation of that system. For example, we have homeostasis, right? So the activity of our body is like generating the same conditions in which the body itself can continue operating in the same way. So like there is this form of like circular causality. So these nested levels, what they actually do is that they are being informed from the bottom up and the top down. The top down is constraining the actions of the bottom, and the bottom is like the activity of the top is like it cannot operate without the bottom level. It is informing it. So these operations need not be like stable across time. They only need to be metastable. So they have this nested character in which you have a coherent system which is composed of other subsystems all the way down, and then each of these operations are like local, transient, and functionally meaningful. So we can use them in like graph theory as nodes because they are transiently stable. So the fingerprints of this is like they have the concept of RTPs. So these are like EEG shows brief patterns of stability, which are called these rapid transition periods. So when we are looking at EEG, we have different ways of pre-processing the data. So usually what happens is that sometimes we experience these sharp discontinuities. And one method is to like completely remove all of them from the data in order to like view what the pattern of the underlying waveform looks like and treat them as like artifacts of the experimental process and not arising themselves from brain activity or viewing them as random like firings of brain activity. So like this view actually says that no, we should take these rapid transition periods as like functionally useful. So what we have in functional correlations is that either you compare the phase lag between different like EEG nodes, or the waveforms that we have a phase, and we find out the correlations of the phases. If they are phase log, it is assumed that they are corresponding to like some task or like whatever we are studying. And the other method is like look at the amplitude correlations. So if they are like correlated in time in their amplitude, we can actually treat them as like corresponding to phenomenology. But with this you say that forget everything that happens between these RTPs. Just look at the RTPs. So whenever we have like a stable object which is forming, like in brain activity, you will have a phase transition which will like propel the system into a stable state. But what is actually important and is the clue is that all of these actions need to happen at the same time. Whenever I'm viewing any object, all of its micro representations, its micro objects, and the overall abstract representation has to cohere together at the same time. Like we cannot parse our experience into like discrete, these continuous steps in which all of these objects are like gradually constituting themselves. So what we will see is that these RTPs are actually showing this waveform in which the entropy is increasing and then suddenly decreasing and then stabilizing. So what this means is that when you are moving from a highly ordered state to the critical point, first of all, you loosen the constraints and the correlations among different regions. So you have a temporary increase in entropy. And then once you reach the critical point in the discontinuous region, you get a phase transition and you like decrease entropy once again. So like this is why it has this kind of a shape. So these RTPs show these kinds of patterns in information, entropy, and dimensionality. So this means that they are actually critical phase transition points. So what we can do is that we can have a new definition of functional connectivity in which you measure the correlations between coincident RTPs. So if you have like 5 or 6 RTPs at the same time, it means that the subsequent section of all of these different temporal regions are actually forming the same mental representation. And if they are not coincident in time, which means that this coherent object which is forming is like does not use those activities. Like this will actually form an ensemble which will give you like all of the micro ingredients and the qualia of one object. If you look at the functional connectivity through these RTPs. So you're not finding correlations in the waveform shapes or the amplitude or the phase. You're just looking at the RTPs. So this is binding by coincidence in time, not the other definition of coincidence, coincidence in time, not these waveform similarity metrics. So whenever all of these RTPs are coincided, it actually gives you synchrony, which is defined by the timing of operations, and not by these continuous oscillatory locking or like phase transitions. So these can allow flexibility, reconfiguration, and coexistence of multiple patterns. So if everything is happening inside the brain, and like the brain is like this uniform medium in which neural activity can propagate, then how in phenomenology do we have very clearly demarcated like stable objects which are not interfering with each other? For example, if you take psychedelics, what happens is that you get hallucinations in which your percepts are morphing and merging into each other. But in normal waking consciousness, this does not happen. So this means that you have to have coexistence of multiple patterns, even if they are implemented on the same substrate and they do not interfere with each other. The only way you can have this is because they are not related to each other depending on their substantial instantiation, but they are actually a part of the same kind of RTP coincidence. So in this RTP coincidence, if you draw every waveform, you will have these multiple regions functionally connected at the same time, which are actually forming that object. And no matter what other activity is happening in the brain, it will not interfere with this because it's not coincidence with the RTP. So this solves the interference problem along with the binding problem. So then we have these instantaneous coalitions of operations, and this entire ensemble is called the OM, or the operational module. So their theory is that this actually is a neural correlate of percepts or thoughts or images. Every abstract object that we have in our thought is actually an operational module. So the combination of all of these operational modules forms the like subjective space and time that we experience, because you need a coordinate system in which to arrange all of these operational modules together. So this is what corresponds to what is present in awareness, and this experience is like relationally structured by these different operational modules. So it is like more the distance metric that we're using is like phenomenological distance, not the Euclidean or physical metrical space. So this is how it happens. Like first of all, you have a mental object, then you undergo a phase transition, another one appears, then you undergo another one. So this actually experience is continuous at our scale. But if you go into the micro scale, it is a prediction of this theory that it is composed of these discrete moments of experience which are all like temporally succeeding each other, and they are like separated from each other from these RTPs. So this continuity in our experience arises because of this rapid succession and these overlapping OMs, and RTPs mark their boundaries. So like they can also say that if you view the minimal level of separation between two RTPs, you can actually find a measure of like the time atoms of our brain. Like what is the minimal amount of like objective time that the brain can experience as a single moment. So the brain does not encode experience because it is actually composed of these patterns. Like these patterns are not representing anything in a symbolic manner. They are itself what is being represented. So these OMs form these structured and hierarchical levels, and these lower level and high level operators are related to each other in an autopoietic, like mutually referring, implicating way. This allows for complex thought, imagination, abstraction. And when you have anesthesia or anything in which consciousness disappears, what happens is that the critical regime of the brain changes. So for consciousness, you require this maintenance of metastability, and you require this coherent operational architecture. When you have excessive coupling, you have rigidity, or insufficient coupling, you have randomness. So if you view the neural activity of patients who are brain dead or in a coma, perhaps the neural activity will not have like these critical phase transitions, and it won't obey these power laws. So this is actually another prediction of the theory. So to conclude this talk, consciousness it depends on critical operational space-time. Conscious experience is not continuous. It is composed of these discrete sequences of metastable presentation states. The unit of mind is not the neuron nor a network snapshot. It is actually a temporarily stabilized operational module, which will have these scale-free correlations, the power laws, maximal information repertoire, and sensitivity to perturbation, which can actually land it into different states. And then you have binding and unity, and the Gestalt character of experience arises from these event-based RTP correlations, synchronization. And the brain does not represent experience, it constructs it through coordinated field dynamics. So consciousness is like an act. Like it actually goes well with the enaction theory of Maturana and Varela. So it is enacted, not encoded. So perhaps we need to move away from the computational metaphors in order to like form a holistic picture of what consciousness is actually like, rather than imposing our own preferred analogies on it. So consciousness is therefore a physical phenomena instantiated in a hierarchical, metastable field architecture. With that, I conclude my talk.
Actually, can you go back one slide, please?
What's that?
One more? Here you were saying about the difference in metastability in states of unconsciousness compared to consciousness.
Yes.
What would you predict happens then in a psychedelic state, as you alluded at before?
Okay, so in psychedelic states, what you have is that you don't lose consciousness altogether. So what happens is that, for example, in LSD, for example, you have these hallucinations. So what is actually happening, I would predict according to this theory, is that since your perceptions are morphing into each other, the number of operational modules integrated together into a synchronous like ensemble, like the number of RTPs coordinated together, is actually increasing, because you need to have this separation of these synchronous events in order to have stable objects not interfering with each other. But in LSD, for example, what you can have is that the systems are moving towards disorder. Like if they completely move towards disorder, then you would not have consciousness at all. It would just completely disappear and you would go into a coma. But it actually increases the critical parameter, which is actually modulating criticality. So it moves slightly above criticality, and like then what happens is that these operational modules start integrating together in ways that are not like maybe evolved by evolution, and then they start combining and interfering. So this like explains it somewhat, but not completely, because in LSD studies what you have is that sometimes they say that insights actually you get more insights while on these psychedelics. So this can mean that there is no one single parameter which is modulating criticality. Criticality is also a context-dependent phenomena. So you can have criticality relevant to different functional regions. So some regions which are like completely separated from each other might reach this critical stage in which they get more functional connectivity during that time period. And like this actually depends like what critical parameter you are using for the criticality. I'm not sure if I answered your question, but
I think, how about we take maybe 5 or 10 minutes, you can relax your voice, because I think there's many points that are interesting for discussion, and then we can have perhaps just a couple of questions and a bit of discussion, and then we go home. Is that okay? Yeah, and everybody can take a breather. There's some sort of awareness, but it's maybe not conscious.
Yes, but then the experiment they used to know if an animal is not conscious but more aware, like it has awareness of themselves. If they experiment with the mirror and the spot, and like lately they discovered that a type of fish did pass this test. So it opens another conversation about consciousness, awareness in the animal kingdom, the level, the different types of levels that animals can have, because they obviously don't have the same level as humans. So this is very interesting to simplify it.
if you were to really go inside this rabbit hole, there is a book called The Sentient Cell, and the authors are arguing that even cells have some form of awareness. But like that's like I haven't studied that book, so I don't know.
No, everything comes from the cell, of course.
Yeah.
This is what. Do you remember when we had this lecture from this? I don't know if you were there, from Michael Voss. He was here. He gave a lecture when I was giving the lectures.
Yeah, I was not here.
What he was saying is like the memory is in the synapse. He did like some experiments. Who was in the lecture? You were. So he was like, he did some experiments with mice and with cells, and then at the end what he claims is that all the memories are stored in the dendrites. Yes. So very little. Of course you go to the molecular level. I'm sure there is a molecular explanation.
There has to be.
Huh?
There has to be, but also what you said before, it's true that maybe when we speak about consciousness, we have to say also that what did you say, the whole is
The whole is greater than some of its
even more
parts.
than the sum of its parts.
Yeah.
Exactly. So that's what you get from this, right? The macro level, it's not just the sum of the micro levels, but it actually gives you something else.
Yeah,
Which
something
in this
else.
case,
Yes. It's not just an aggregation of the lower levels, but
Right.
something qualitatively new arises.
But of course, without the micro level, you would never even
Yes.
get to the macro state.
Yeah.
And can you go to the last slide?
Okay.
There was
one?
like a sentence,
Uh,
like the encoding or decoding. No.
the last slide. Okay. Yes. Go.
This one, the consciousness is
Enacted now.
not encoded. Because of course you would think like, in neuroscience you would say everything is encoded. Encoded and decoded, for me it's like, yes it is. But what you are saying is not like this, yes?
Yes, because consciousness
What do
is.
you mean by enacted?
Okay, so like let's imagine an analogy in which, for example, you have a very hyper-realistic video game that has the representation of the environment, and you can move around it. So if you look at the physical implementation of that system, everything is being represented by the bits that are being stored in the hard drive or the RAM. So everything is literally being represented there, and then through various transformations at the end it is transformed to like pixel values on the screen to be able to make sense for the interpreter. But in this method nothing is being encoded in this way. Like it is the actual topology of all of those electromagnetic fields which temporarily come together to form like a coherent gestalt, and that coherent gestalt is not a representation, it is like the actual electromagnetic field topology of those electric fields, which actually like it is the texture of experience itself, the qualia itself, and not like a symbolic representation of it. Yeah.
I didn't get it. Can you say it again?
Like if you have like interfering electric fields and they are being
Of the brain, so literally.
yeah literally, and they are being like the phase transition that happened to bind those various electric fields into a single subject
So the phase coherence, you mean?
The synchronous RTPs.
Okay.
Like not.
These are time points.
These are time points. So only those regions which coincided with that RTP actually go on to construct that perceptual object, right? So that perceptual object is like formed by those different neuronal assemblies which are participating in that synchronous operation.
And then its content is given then by amplitude frequency. What
Yes,
what we
the content is
now
given by the
time
amplitude.
point that actually makes it be.
The Gestalt character comes from that, and the actual texture of that comes from the amplitude variation and everything. But still, it still does not explain why we have different sensory modalities. Like we have vision, color, like smell, and all of these other five senses, also proprioception. But like, what actually differentiates the waves which are instantiating these different things? Because you can vary the amplitude and the frequency of the wave in order to like represent different colors. So like I use the analogy of representation for this, but like I read some papers in which they are saying that even at this level there cannot be representation, because that same variation in amplitude and frequency is giving you no information as to why that particular section of the EEG waveform is corresponding to a color or a sound or a texture or anything else. It does not explain the sensory modality. So perhaps it has some other characteristics which we don't know of currently.
The micro level maybe then, what it makes it up, where it is in the brain, what the neurons like, what kind of neurons.
What kind of neurons?
Then maybe this is the extra information that is missing.
But I would go more towards, I think, the OR theory of Roger Penrose. So as I was saying, like I explained the concept of RTPs, right? So intuitively you can think of them as phase transitions. Like we know that they are phase transitions just because of these graphs in which we see critical behavior over here. A sudden, very small change in entropy on the positive direction when these constraints are loosening, and then a phase transition into like a more ordered state and the offloading of entropy to the environment. So that's how we know it's like changing. But for the segments between the RTPs, now what happens is, if you look at the other slide, all of these ensembles can be correlated into like a single perceptual object if they are actually preceded by this coincident series of RTPs. Like the RTPs have to be present in the same moment in time in order for all of these activities to be forming the same object. Now, if, for example, these two had an RTP over there, then they would be composing a different object. They would not be forming the same perceptual construct. So this is how the brain differentiates between different perceptual constructs. Like if I'm seeing you two, you are forming two coherent objects, even though you have a microstructure. But I am able to separate you two. So the activity in my mind would be like a different ensemble related to like this coincident train of RTPs for you and for him, and they do not interfere with each other. And the pattern that we have between is like it can also be composed of further sections of these RTPs. Like you can have micro RTPs between them as well. So to have that hierarchical structure. And the actual pattern is a standing wave, and that can actually, like, I'm having to use computational language again, but encode the texture and the what it is likeness of experience. Like different phenomenological characteristic of experience can be somehow encoded by the shape of the waveform.
So intuitively, the point is that we do not care about amplitude, we don't care about frequency, we care about when there is changes and whether these changes are the same throughout the different regions in the brain, which would result in seeing a coherent whole rather than some of some parts.
Yes.
That's the intuition.
Yes, that's the intuition, because
I think this makes a lot of intuitive sense, and it will be interesting to see, for example, I'm not sure if you had a look at this, but in stroke, when people see things in stroke, and there's these images, have you ever Googled it, or like what it's like to have a stroke?
perhaps you can explain it to us.
And there's, I can't, there's some images if you Google it, and it's like a lot of things, they all look a little bit familiar, but nothing makes sense. Like you look at a chair and you can describe the four legs, and then you say there's four things that does not look like anything.
Yes.
So what you're saying is exactly like maybe there's a shift in this metastability because of some structural damage or something.
Yeah.
Like at the checkpoint, gets like.
Yeah, actually that makes sense, because imagine that you're having a stroke and some like artery in your brain is like clogged for a little moment. So that will like disallow that particular neuronal assembly from like firing in the exact sequence they have to fire to have the RTP at the exact same moment. So if you don't have the integration of those neuronal assemblies into the experience, perhaps you cannot form a gestalt. So the gestalt breaks down, and then you see these the like simplistic objects, like the components of the chair, for example. Or if you're seeing a face, you might be able to see the nose or the lips or the ears, but not the face as a whole. The gestalt breaks down.
So when you are unconscious, all this will disappear?
Yeah, that's the prediction of the
So
theory.
what would be like the interface? So you are conscious and then you are unconscious. So could you predict, you know what I mean?
Yes. So you can predict it by checking for the
By
fingerprint
checking this or by something?
by checking the fingerprint for criticality. So what you have is these power laws, right? So actually, when you are having these neuronal avalanches, I did not mention in that in this talk, but like I read about it when I was preparing. So the neuronal avalanches always show power law characteristics across scales when the brain is conscious. But when you are in a coma or you are in a vegetative state, what you can have is that you might still have these neuronal avalanches, but they do not have these power law characteristics. And at
But
the same,
it's not black and white, yes?
yeah, it's not black and white.
So
Like
you
there
are
is.
conscious and you are unconscious. But it's not like one or the other. Is there like an in between?
Yeah, because the resting state tries to maintain you around the critical point. And then the way to lose consciousness gradually is to either move in the more ordered direction or the less ordered direction. So the more you move, you stray far from the critical region, the more you lose consciousness gradually. At the end, like at every end of the spectrum, you won't have enough information integration to be able to support experience. And there is also one other theory. It says that actually what happens is that we cannot claim for sure that consciousness completely disappears. Perhaps we are just losing the ability to verbally report our experiences to others. So perhaps in vegetative states, they might still have some minimal form of consciousness, but they might not be able to communicate that in any way.
Well, this coupled with memory, because then after coma, people don't tend to remember that. But
Yes.
that might be.
But
We don't
sometimes they
know.
do remember.
Sometimes they do remember, and there's different stages of unconsciousness as well. And one thing that your question,
Wait, because I know somebody who was in coma, and he was somebody from the north of Spain. Yes, he couldn't speak Catalan, this person. And then because in the region of Spain where he was, the hospital was not good enough, they sent this person here to Barcelona. And then he was in coma for 20 years. And when he got out of the coma, he could speak Catalan.
Wow.
he had learned.
So he learned the language when he was in coma.
But there's
this is
but
a guy I
there's
know.
minimally conscious.
He was like,
state.
maybe he was like, what you said, like there is like a state that is,
Minimally conscious,
Yes.
so, as opposed to a persistent vegetative.
Well, no, not about that. I think well that a lot of times you are like
Modeling, we have certain ways to model the local dynamics of the different brain regions, like Astray said. So finding the bifurcation parameter, the balance between noise and oscillation. And this is a study that did exactly this. So changing this bifurcation parameter, modifying somehow we called it here in this paper, they call it microstates. So the different states within the brain within brain dynamics. And they show that by modifying the bifurcation parameters, somehow they were able to wake up the in silico brain and put it back to sleep. And the intuition here is quite simple. So if you increase oscillation from sleep, you go from sleep to awake. And if you apply noise to an awake state, you actually go into a sleep state.
But how
Eh?
does this work? Like by putting some sound, you induce some.
No, so this is done using modeling. This is not in a real brain.
Okay.
And the idea is
in
to-
silico brain.
This is using simulating electric or magnetic simulation in the brain. You have like electrodes, and then you do like this. You can implant electrodes also. Humans, it's not so commonly done. And it's a step towards using exactly what Asher was explaining to wake up people from coma. Because if it works for sleep and awake, maybe
it can work for coma as well.
But one point that you said at the beginning, these states in sleep, for example, is already different from coma in an important way, namely that it is much more stable.
Yeah.
So a little perturbation is very difficult to make you transition in a state if you are so far away from the critical point, as you were saying. The critical point is so that, exactly what he said, so you can switch states super fast.
Exactly.
But if you're super far away, then the perturbation has to be super strong.
So you need the people in coma to get away from the critical point.
To go away from, maybe this would say to go away from noise and go more towards observation. And then the question is, where do we stimulate, how do we stimulate, how strong? And then in modeling, well, because ethically, I mean, we can't really just take a machine and go like,
but also there's like this asymmetry in this explanation, because in the critical point you can approach the critical point from both ends. So like if you want to add noise to like make it approach the critical state, what you have to have is like a very ordered state. So sometimes what happens is that, for example, if you're playing chess or like you're having a very like difficult cognitive task, and you go out and have a walk, and then you come back and the insight snaps in your mind. Because when you're in that state, the information from the environment and the noise is like, it's not that much compared to a walk. So like you are constrained in those stable configurations and your repertoire is limited. But when you go out, like sometimes this random information can like nudge you a little bit more to that critical state, and then you'll have other options to explore. And other insights may also crystallize because of this. This also explains this.
One question, how is it in monkeys or like other mammals? Is it similar? Do you know, like, do like monkeys or like dogs, do they also go into like coma, or are they conscious?
Yeah, I think they are conscious.
Is it similar? Do you know?
I think I have not read about this directly, but what I would predict from this is that the only difference between us and the animals is that they are also conscious, but the problem is that we have these very high level representations as well. Like we have this nested like Russian doll character in which.
Can you show the figure again?
Which one? This?
What you're saying, the Russian doll one?
Oh, okay.
Yes.
Yeah, this one. Yeah. So like perhaps we have access to certain macro level states that their minds do not have access to.
They don't.
Yeah. And perhaps like the architecture of the mind and the substrate is important in this, because in order to achieve these high level states, you would have to have a system in which a very large influx of energy is like coherently stabilized into like a stable state and does not instead destabilize the state. So perhaps in evolution, the complexification of the mind and the ability to form these higher level percepts is related to this process, in which you are able to harness this energy and convert it into free energy, instead of like letting it destabilize your system and get it saturated. So perhaps they are actually operating at this level, and we have these other levels as well.
And now a really basic question. What's the difference between consciousness and awareness?
Okay. So consciousness can be likened to the what it is likeness of experience. Like the actual contents of experience that we experience, like different types of colors, sounds, textures, smells, everything that we call qualia, like qualitative characteristics. And awareness is like in this analogy I told you about the internal coordinate system, right, where everything is integrated. So perhaps awareness can be likened to the foundational characteristics of a system, like this space in which every consciousness element can be assigned its proper place, both temporarily and spatially. Yeah, the arena in which everything is integrated is awareness.
So awareness requires consciousness, or
I think awareness is the like minimal condition to have consciousness.
You would make very many people mad with this.
Yeah.
So, so some people would even define consciousness as being aware. Other people would say it's awareness plus memory, because otherwise you cannot really be. But again, it's who knows. And then what you said about awareness of consciousness is awareness.
I think what they have is like they want to include the persistence of identity within consciousness. So for example, what you can have is a system in which there are these conscious moments of awareness, everything is being experienced, but there is no memory and there is no continuity within those changing chains, which will actually give rise to a subject which will be able to recall its own personal history. So for example, if our short-term memory is like shrunk down very small, so we will be experiencing everything, but we won't be able to recall anything. So like, we can't say that we are like we have one persistent identity across these moments. So like, maybe the construction of identity is like an emergent process which is not there from the beginning, and some conscious systems have this capacity and some don't. But both are conscious. It's just that one cannot report their identity and one can. Maybe.
Because a plant, you could argue, is also aware of the sun somehow, right?